Good morning and welcome to today's webinar, Measurement Risk and the Impact on Your Processes. My name is Sarah Wallace from Transcat and I'll be your moderator this morning. Joining us on the call is Howard Zion, Transcat's Director of Technical Operations, Jeremy Sims, Transcat's Supplier Quality Analyst, and Dan Colvin, Wind Energy Account Manager with Transcat. Today we will spend the first part of our time in presentation and then end the call answering your questions. Anytime during the presentation, you can send questions through the question box to the right in your webinar controls. If we happen to run out of time before getting to all the questions, we'll follow up offline to the email or phone number you provided at registration. I also want to mention the webinar is being recorded and will be available for viewing through transcat.com. At this time, I'm going to turn the presentation over to Howard.
Thank you, Sarah. And thank you to the webinar audience for taking your valuable time to listen to some of the concepts that I think would be useful to you. And hopefully it'll stimulate some thought on how this can help you in the long run. Let's get started. We're going to cover a few concepts today, and these are only conceptual. I'm not going to go into any detailed examples in this presentation. We'll talk about what measurement risk is, how risk creeps into your manufacturing process, how it can creep into the calibration process, and then the calibration results and the impact that has on your manufacturing process. And then, as Sarah said, we'll get into questions and answers. So measurement risk is a probability that the instruments you're using and making decisions upon for your product are not what you think they are. That maybe those instruments are incorrectly influencing that acceptance decision of your product. So if you're accepting bad product, that can lead to negative results ranging from simple consumer dissatisfaction to something more extreme like fatalities and lawsuits. But if you're rejecting good product, that can lead to negative results as well. Possibly unnecessarily scrapping work, parts, components of your product, or reworking those components of your product, and that's wasted resources, as well as evaluating out-of-tolerance results and having to use your resources for that function. It's possible that some of your rework, scrap, recall is related to the result of unbridled measurement risk, and you may not even know it, you may not realize it. So how can you determine if measurement risk is a problem in your manufacturing process? Let's flip that around and talk about, instead of measurement risk, talk about measurement assurance. Measurement assurance encompasses a number of assumptions in your manufacturing process, and I'll list 10 of these. The first one is product acceptance. Did you make the right decision about the acceptance or rejection of your product or a component of your product while you were in the manufacturing process and in your quality acceptance process when you were using instruments to make that decision? The basis of that decision is the instrumentation that gives you the quantitative values. Suitability for intended purpose is making sure that you've selected the right instruments for making those decisions about your product acceptance. Instrument application has to do with using the instrument correctly. You may have selected the right instrument, but are the things that you're doing that cause errors in the measurements? A term that I call beginning of period reliability, and that is the calibration of the instrument prior to using it in your production process. Does it meet its performance expectations prior to you putting it into the place? And then the end of period reliability is at the end of the calibration cycle, that subsequent calibration, and does it indicate that there was any error in the instrument when you were using it to make decisions about the process? And then the calibration process itself. Were those calibrations executed correctly? And I'll go into more detail of that in a few minutes. Following the calibration, your nonconformance review. If your instrument failed to meet its performance specs, then your quality system probably has a review process in place that evaluates whether that had an impact to the decisions being made about the quality of your product. because that changes the quantitative values that you're relying upon. And then the accuracy of that nonconformance review. How thorough is it? Did it miss the mark on making sure that it, evaluates whether those errors in the instrument actually had an impact on where it was being used? And then risk mitigation. Any negative result from the impact study and how that's mitigated to remove or reduce risk in your product. So if you put a value on each of these 10 areas for measurement assurance and scaled that from a 0 to a value of 1, you could come up with the total overall health of your measurement assurance program in your production process. And you do that by multiplying the values together. And that's kind of like a reliability figure. So it would be 100% if each of these were at a value of 1. I've given a few examples here of how that might change. For example, if all of the areas had a value of 1 assigned, but the instrument application indicates that in some situations it's being used incorrectly. You have the right instrument for the job, but there's something your personnel are doing in the process that cause errors, and you evaluate to figure that this has a value of 0.95. And also that your accuracy or thoroughness of your nonconformance afterwards, when you find out that you have an out-of-tolerance condition, isn't as thorough as it needs to be. Let's say you give that a value of 0.9. Your overall health would be 85 or 86%. In the next example, for example 2, everything is good except for the calibration process where, for example, half of the test points were checked based on where the instrument is being used and how it's being used in the process. So if you didn't check all of the functions or all of the ranges of an instrument where it's being used, you've lost traceability in your measurement. You have no idea about the confidence of your measurement. So let's say half of those are being checked, you give that a value of 50%. Overall it drops to 50%. Example 3, reliability would say that you don't have an NCR review process at all. I've seen situations like this, although it's not very common. But that's the point of the whole traceability chain of measurement, is not only to make sure that you have equipment that's suitable for the intended purpose, but make sure that you're using the end result of the calibration of those instruments to determine whether you have an impact to the product. And if you're not reviewing the results of those out-of-tolerance conditions, and in some cases intolerance conditions that are close to the limit, then you're not doing yourself any favor. You're throwing away good money for the calibration process and the use of the instrumentation to control your process. So I want to talk about some specific categories here, starting with suitability for intended purpose. Again, when you're looking at selecting an instrument to make measurements in your production process, you've got to take a look at the parameters that you're measuring in the process and make sure the instrument can measure those same parameters. You also want to make sure that you have a good, accurate product that can make stable measurements for those readings. What environment is it being exposed to? You've got to check that as well as part of the suitability for intended purpose, making sure that the instrument, as stated by the manufacturer, can work in the environments and that it's being used in, and that you're checking also to see if there's an impact to its accuracy based on the environment that you're exposing it to. And then the other thing is the experience of the operator and their ability to use the instrument properly so that you don't introduce other errors in your measurements. The application, and that's what that leads to, is the correct use of the instrument. Incorrect use can introduce the errors that can cause you to have a different outcome of your decision whether the product's good or bad. A few examples here. If you have a platinum resistance thermometer with an indicator, the way that has to be used is that during the calibration there's a set of coefficients determined that have to be programmed into the display. There are some types of connectors where that's automatically programmed into the connector and it removes the operator error. Some of the older units have that, though, where you have to enter the coefficients into the display. And if that is left at the old coefficient values, or the wrong coefficients are plugged in, or the probe is changed out without changing those coefficients, you're going to get incorrect temperature readings, and you're going to make wrong decisions about your product or your process. A set of calipers. Those are easily picked up and moved around and possibly dropped, and if you have nicks or burrs on the jaws, that's going to shift your zero or possibly affect your readings. Torque wrenches. Without having any damage to the instrument at all in its normal use, there's enough influence from how the operator uses a torque wrench that you can introduce up to 10% error in the reading. And a good gauge repeatability and reliability study would indicate how much error you have. Drive block calibrator is another good example. There are so many different types of influences an operator can have in not transmitting the temperature properly. From the wrong size insert for the temperature probe being used, to not compensating for axial uniformity, which is from the top to the bottom, versus radial uniformity, which is from well to well. Overloading it, putting too much into it, can cause the temperature transfer to be incorrect. So you may think you're generating a certain temperature from a drive block calibrator, and you're not actually getting that. And that introduces error, which changes the result of your testing of your product. An oscilloscope, for example, if you're using it above or near its bandwidth limits, can cause a frequency cutoff for the amplitude, and you get a different reading than you think you're getting. And again, you're making decisions based on that for your product or your test of your product, and that can change everything about whether you call that good or bad. Beginning of period reliability. Here's some things to think about. When you purchased the instrument initially, did you put it right into production without having it calibrated first? Did you rely on a production cert, which is not always a guarantee that it meets all of its performance specifications? Was the initial calibration 17025 accredited, which brings a lot of detail behind that? We have some white papers on that if you don't know the details of 17025 accreditation. Many times OEMs are not accredited. And then when you recalibrate the instrument, was it returned to you in a condition that was maybe close to the tolerance limit? How long will it maintain that condition through its next cal interval? So those are some of the things that you need to think about that can cause non-conformance reviews to occur, which cost you money. End of period reliability is the most critical information you can have, because now that you've used it for that calibration interval in your process to make decisions about your product, here's the final result that tells you how it performed, how that instrument performed, whether it maintained its tolerances. Was it found to be out of tolerance, or was it in tolerance and close to the out of tolerance limit, which can still have an impact on your decisions about the quantitative values that it provided. And then this gets into the lab's uncertainty, measurement uncertainty, and how this impacts that close to being out of tolerance region. How do you use this information to determine how it affected your product or your decisions about the product or tests that you ran during the last calibration period?